everyone, and welcome to the first session of talks at ESMARConf. We've got some great talks going on this morning. Sorry, that was my dog. So I will start off by welcoming our first speaker this morning. So this session is on automation, particularly text analysis tools for evidence synthesis and meta-analysis. And our first speaker, Aaron, is going to talk to us today. I'll just get his talk up. Okay. Hopefully you can all see that. Great. So, sorry, one sec. Technology issues, as always. Here's Aaron. Thanks very much.
So, good day. My name is Arindam Basu. I am an associate professor of health sciences, and I am going to talk about my presentation on using computational text analysis to filter fast-pass title and abstracts in systematic reviews. So let's get started. Now, one of the things that we know about systematic reviews is this, that they're quite time-consuming processes. Although systematic reviews are excellent for generation of evidence, and therefore there's a lot of interest, a lot of people do them. But one of the most important point where we spend a lot of time is in correct selection of primary studies. And selection of primary studies are essentially on the basis of titles and abstracts. But before you do that, you need to have a protocol, and then you need to have some sort of a way in which you can search the studies in literature databases, and then you select the studies on the basis of which you want to build your systematic reviews and meta-analysis. But after you obtain the your total number of primary studies, it can often go up to hundreds, and sometimes I have seen in my previous experiences about several thousand studies need to be analyzed on the basis of their titles and abstracts. This process is time consuming and it is prone to errors. So one of the ways in which people do this is this, that if many of us, if a team is conducting the systematic reviews, then we have open our protocol, we select keywords from our inclusion and exclusion criteria, we read each title and abstract carefully, and on that basis we select whether a particular title and abstract fits our purpose or we have to reject it. And on the basis of this, we eventually create what is known as a Prisma chart, and this goes into there. So can we use computational text analysis or quantitative text analysis, where we can use a computer and algorithm to go through the process and make it faster? In this example, we will be using a particular type of quantitative text analysis software called Quanteda, which was written by Ken Benoit. It is a free package which you can install in our software, and you can work. So we used a study where we wanted to see what is the effectiveness of mindfulness meditation for anxiety relief. We ran a search on PubMed, and for this example we are only going to use PubMed, and we found that there were 95 studies. They were all English language human studies, and we got that study in the form of CSV file. So then what we did was this, that we loaded Quanteda, readtext packages, and tidyverse libraries onto R. And then we used this particular version, the readtext function, in order to read the base file, which contained the URL of it. and we assigned a text field which was title. The text field will be the one which will be processed. The next step was that we converted that PubMed object into a corpus, and the corpus contains all the essential information along with the text level, along with the document level variables in it. Then we converted the entire corpus into a set of tokens, which means that we split up the individual sentences, which were the titles, essentially into individual words. And then what we did was this, that we used several options so that we removed common words, which were like stop words, English language words such as a, and, the, etc. Then we created our own dictionary, which contained all the terms that were included, that we wanted to include in our inclusion criteria, so that we could put together our inclusion and exclusion words that the software would then go and search in the titles. And then what we did was that we created a document term matrix, or document feature matrix. In particular, in case of Quanteda, these terms are referred to as features. And then we used a dictionary that we created earlier with the document feature matrix. And then what we did was that we looked up the terms and classified them whether they belonged to the inclusion criteria that we set up earlier. So this to two tables. One was a features table that you can see here. And so these are the terms: mindfulness, randomized, meditation, anxiety. These are the statistics that you get to see, that you can see that from here, we see that there were 46 studies that were randomized controlled trials, the ones that we wanted to see. 55 out of 95 studies contain the term mindfulness. 22 studies contain mindfulness based. So there's a slew of around 77 studies that contain the terms mindfulness, but not all of them were randomized controlled trials. And we see that the outcome term anxiety was found only in 25 out of 95 studies. So you can see that very quickly it helps us to narrow down on the terms the studies that we want to see. So in terms of the outputs, you can see that combining these various terms, we are able to generate the outputs that we would like to see, and select the studies that would be useful for us. This is only a header that I'm going to show you. So then you can export the outputs to filter studies based on the basis of titles. You can see how they can be rapidly narrowed down. You can use that on the abstracts, not just on titles. And computational text analysis can be used for even full text articles, such as PDFs. I must say that this is very much a work in progress. If you want to take a look at the GitHub repository, you can go here and you can work with us. Thank you.
Brilliant. Thanks very much, Arin. Our next speaker is Martin Westgate. Apologies for everybody who saw my face taking over Arin's presentation there. But we'll move on to our next speaker, and questions we'll take at the end in a panel. Martin, you're presenting live, right?
Yeah, lovely. I'll give it a go. Now, I'm hoping everyone can see my screen. Neal, you seeing that?
Yes, I can see that.
Yes, lovely. Okay, wonderful. Hi, everyone. I'm Martin Westgate. Welcome to Sunset in Ngunnawal country. That's Canberra in Australia. I know it's early for you, but it's quite late for me. Very happy to be here, though. So I'm here to talk about revtools, which is a piece of software that I wrote for screening in R. And I'm going to talk through the history and the status as it is now, and give you some hints of what's coming in the next release. So, interestingly, this is moving without me, so I'll have to keep up. Basically, this is based on revtools, came out of a piece of work that I did back in 2014 and 15, which was where we were trying to do some reviewing where, to be frank, we just didn't want to read all the literature, but we wanted not to do a systematic review. We weren't trying to replace that process, but we were trying to summarize the information that was in a body of literature without having that initial step of having to read thousands of articles. And so We recognized that was a different process from a review, but we thought it'd be useful. And to do that, we came up with some scripts that we wrote a paper on, and then that formed the basis of what went into revtools. That led to the point where it was published last year in Research Synthesis Methods. And to give an overview of what it was built for, revtools its primary function is to combine topic modeling, which is kind of text summary statistical approach, with screening. So this is just a screenshot, so it's not an interactive version, but you can literally drop some data into this from Web of Science, PubMed, Scopus, that sort of place, your own EndNote library. It'll read it in a clean way, it'll run a topic model on it, and then it'll show a visualization of which points are where, and it'll enable you to select or deselect, or exclude rather, individual articles or whole topics. Sort of by mistake, mistake is the wrong word. While I was writing this, someone said, "Oh, that's great, but it would be nice to just screen articles manually." And so, sort of almost as an afterthought, I wrote some Shiny apps that enable you to screen titles or abstracts as well. So that functionality is in there too. And that's basically what it does. It's quite simple in a lot of ways, but it's also been designed to be fairly easy to use. So that all seemed pretty good. I then, changed jobs and ran out of time to do much coding, and now I'm coming back to it. And it occurs to me that there's a few odd things about the interface. I'm quite proud of it in general, but there's a few things that could be improved. One of which is that the workflow at the moment is that you read your data in, you can do some of the processes that you saw in the previous talk about making a document term matrix or a document feature matrix, and you can run a topic model, or you can pass your data to screen topics and it will do these processes for you. That was all initially written by me in R from scratch, and that felt a little inefficient. So we've spun off the data import processes into a different package so that can be focused on separately, called Synthesizer. That was a collaboration with Eliza Grames, and that went on to CRAN last year. We've also started using Quanteda in revtools, so thoroughly recommend you check out that package for text mining applications. And we've switched from topic models as our infrastructure to STM. I'm also doing a redesign of the actual interface, but that's not complete yet. So revtools will look different in the next release, I'm hoping. So that's so basically that's a huge. The code base is smaller for revtools, even though it does more things than it used to because we've outsourced some of this functionality. This diagram looks a little technical, but on the left is saying here's what the CRAN version does. It's the same workflow I showed you before, and the new version is a little cleverer in that you can not only pass your data to screen topics and run a topic model, you can pre-process a topic model and then pass that to screen topics to visualize it. So that's useful if you have a very large corpora and you want to do pre-processing, you want to do your own document term matrices or whatever. You don't have to rely on the defaults in revtools anymore. You can just do your own processing and then visualize it with revtools. There's also some scripts that plot using ggplot the same outputs that you'd see in a Shiny app, but in a static way, so that you can, which is better for publication, for example. The final thing that people here may be interested in is if you're working with a team and you want to decide who in your team that can see which articles, and other things like you may wish, if you're doing this work in experimental context, to see how long it takes people to screen particular articles. You may wish to play with things like the order in which they receive information. You can preload an app. So you literally use this function to say, I want this person to have this data in this order, and then that generates an RDS file which you can email to them. You can send them through Dropbox or whatever, and you simply run the same function as you would on the raw data, but it actually contains the entire Shiny app, and they are then restricted from being able to edit the features of the app. They just do the screening, and it saves automatically to that same file. You can send it back to you. So it's a bit more rigorous for team screening than it was previously, and that's we've been using that in my lab. We're nearly done, I think. So to summarize, revtools is now less just about screening and more a combined process for topic model visualization and article screening. I'm hoping that the new functions provide a wider range, support a wider range of applications, a wider range of people using it. And while I don't want to overcommit, I'm hoping that the next version, which will be 0.6, would have more customizability, because I think that would benefit yet more people. So I'll leave that there. Thanks everyone for your time, and I'll stop sharing my screen so that you can carry on seeing other interesting talks. So thanks again.
Thanks very much, Martin. That was really interesting. Okay, still seeing your screen.
How about now? Is that better?
Perfect. So thanks very much. So I was trying to work out where some noise is coming from. Next up, we have Max, who is also presenting live, I think, from Berlin. Over to you, Max.
Okay, I'm just working out how to unmute myself. So hello, everyone. I'm going to be presenting on statistical stopping criteria for automated screening and systematic reviews, which is work I've done with my colleague Finn Muller-Hansen. Oops. Okay, so we've heard already that identifying studies for an evidence synthesis project can be very time consuming. And there are ways that machine learning can be used to speed up this process. Really, we can train a machine learning algorithm using human decisions to predict the relevance of unseen documents. And we have what's called an active learning pipeline, where human screens and documents, the machine learning is trained using this information. It predicts the relevance probability for remaining documents, and then those documents are ordered in descending order of predicted relevance. And there are numerous studies that that have looked at this and shown that we can save quite some work with this method. But a lot of the time, almost all of the time, I argue, the work savings are only potential, because they're dependent on an a priori knowledge of how many relevant studies we're looking for. And to actually achieve these savings, we need to know when to stop screening. And in the paper that accompanies this presentation, I show how existing approaches to doing this are insufficient. In this presentation, though, I want to make really concrete examples with our code, and probably I'll have to go a little bit too fast for everyone to follow everything. But what we do is we set up here a toy dataset with 2,000 documents, of which 100 are relevant. And we represent these just as a vector of zeros and ones, zeros representing irrelevant documents and ones representing relevant documents. And the thing we're looking for here is recall, which is the number of relevant documents which we've seen, divided by the total number of relevant documents. And obviously we want to keep recall high, because we want to see as many relevant documents as possible, but we usually accept that we won't identify every single document and aim for a target of something like 95%. Although using this framework, this is flexible. If we screen at random, then we will screen 95% of all relevant documents. We'll achieve our recall target, which is represented by this horizontal line, after about 95% of seeing 95% of all documents. If we can increase the speed that we identify relevant documents using machine learning, so I've just done this with probability weighting here, we can identify 95% of all relevant documents after only here just under half of all documents. So we've saved ourselves a lot of work theoretically. However, it's easy to see when to stop if we have all the information. But if we only have, if we don't know how many relevant documents there are, we can't actually scale the y-axis properly. And actually, we might think at this point, okay, we've seen several consecutive irrelevant documents. Let's just stop. However, obviously, this is stopping too early. So we need to find a way to decide when it is actually safe to stop. And what we can do is use a bit of probability theory to infer from the documents that we've already seen something about the distribution of relevant documents in the future. So in probability theory, we use the analogy of an urn with green marbles, which are relevant documents or successes, and red marbles, which are irrelevant documents or failures. And we're drawing these out at random from the urn. And with the hypergeometric distribution, we can calculate the probability of drawing k relevant documents in a sample of n documents from an urn that had n total documents, of which k were relevant. Now, this is good, but we don't actually know what k is. So that's a bit of a problem where we have to do some extra work. So I'm going to have to skip the detail, but feel free to ask me about it or look back at the presentation later. What we do is we do hypothesis testing. We have a null hypothesis that we have not yet achieved our recall target. So if we can reject that null hypothesis, then we can say, okay, it's safe to stop because it's unlikely that we have missed our target. And to do that, we need to have a hypothetical value of k, which we call k tar, which is the lowest possible value of k that would be inconsistent with our null hypothesis. So we can get a p-value plugging all these things in. And what that does is we can calculate a p-value at every point in this red line. And at some point, the p-value will go below our critical value here of 0.05, but we can set this at any level depending on our risk appetite. And so we can say at this point, it's pretty unlikely that we've missed our target. And you can see that this corresponds with the point a little bit after the time when we do actually meet our target. So this is already quite useful, but this is based on stopping machine learning screening and starting a random sample. And that's not very helpful. So what we can do is we can treat previously screened documents as if they were a random sample. So precisely, we treat the past 1, the past 2, the past 3, etc. documents as if they were a random sample. And unless the machine learning algorithm has completely backfired and is giving us documents that are less likely to be relevant rather than more likely to be relevant, then this is a conservative assumption. And we can calculate the p-value at each of these last subsets of documents. And so from this point, the p-value was never low enough to stop screening. So that means that we have to keep going. So we calculate the minimum p-value at every point along this line, which corresponds to all of these points. And here we reach a p-value that means that we can reject our null hypothesis with saving about a quarter of the work. So we tested this extensively on 20 systematic review datasets, and we simulated 100 machine learning assisted reviews of each. Our criteria performed well in the sense that it was reliable. So we missed our target in less than 1% of cases. So it was actually a little bit more conservative than our confidence level that we set. The work savings weren't spectacular, but we've got to point out that these were fairly small data sets. So only the blue dots had more than 2,000 documents. And the way this test scales is that larger proportional work savings are available with larger sets of documents. Okay, and so that's about everything. And to take away from this, you can use this R function to test a vector of 1s and 0s with your some information about your data set and your target to see whether it's safe to stop. Thank you very much.
Brilliant. Thanks so much, Max. So next up, we have Richard Cornford, who's going to talk to us about automated identification of articles for ecological data sets. So please excuse me while I just try to connect.
Hi, I'm Richard, and I'm a PhD student at Imperial College London, working with biodiversity indicators and their data. My work focuses on using these data to understand biodiversity change across space and time, and also how to improve upon these datasets using automated and semi-automated approaches. And this is the part I'll be talking to you about today. As I'm sure you're all aware, a key challenge associated with evidence synthesis, including the collation of ecological data, is the discovery and identification of information sources. Within the scientific literature, there's a vast amount of data available, but finding these articles is currently a largely manual and time-consuming process, which creates a bottleneck in the evidence synthesis workflow. As the literature continues to grow rapidly, manually screening articles will become ever more challenging in the future. I'm therefore going to be talking about how automated text classification, based on the titles and abstracts of papers, can assist researchers in the initial article screening stage by quickly and accurately prioritizing thousands of articles, which helps to ensure that compiled evidence remains up to date and representative. As you can see in this diagram here, there are a number of stages associated with the development and use of automated classifiers. Training and validation are undoubtedly important, but today I want to be focusing on the real-world application and their potential for iterative improvement. I'll be discussing this in the context of two global biodiversity databases, specifically the Living Planet database, which collates information on vertebrate population trends, and the Predicts database, which monitors biodiversity responses across land use gradients. During the training and testing of our classifiers, we find that the logistic regression models perform best, and that these display very high accuracy on our labeled datasets. This is great, but search engines are already capable of filtering and ranking articles given a set of keywords. We therefore wanted to try and assess the real-world performance of our classifiers, comparing them to current standard protocols to get a better idea of their actual benefits. To do this, we conducted literature searches associated with our ecological databases and compared the rate at which relevant articles were found based on either the rankings of our classifiers or the search engines themselves. This figure and our results show that our classifiers outperformed the search engines, with most of the points relating to a particular search here showing that you find more articles per article read when using our classifiers than you do with the search engines. So these results are encouraging, but they're also based on classifiers which have been trained using around 500 or more relevant articles. This isn't a massive data set by big data standards, but it's a pretty substantial library of texts. If you're just starting out with your data collation, you're unlikely to have so many. And so you want to be sure that using text classifiers is still useful, even if you have fewer training data available. We therefore separately evaluated how the size of the training set and the incorporation of new classified texts affected model performance. So firstly, whilst larger training sets undoubtedly improve model performance, even classifiers trained on relatively small numbers of text still display very high accuracy. Furthermore, as you can see, incorporating new classified texts does boost performance, and in particular, upweighting new negatives further is the optimal setting. This is likely due to our screening protocol, whereby the new negative texts that we've manually classified were predicted to be highly relevant by either the search engine or our own classifiers. As such, these texts are likely to be in some way highly similar to truly relevant texts, and so incorporating them into the model fitting better allows us to determine the boundary between relevant and irrelevant texts. In combination, these results therefore suggest that it should be possible to quickly generate useful classifiers from models trained with only a modest set of initial texts, and then you can subsequently improve their performance by iteratively updating the training data. Finally, I just wanted to briefly outline some potential directions for further work in this area. So one of these is to facilitate the wider adoption of such approaches. We're in the process of creating a user-friendly Shiny application, which wraps around the Python classifier code. And so not only could you train, apply, and save custom classifiers here, but you could also add in additional functionalities, which might further aid human reviewers. One such example of this could be model modification, which might be able to mitigate some biases which may be present in the underlying training data, and could subsequently undermine analyses conducted on the collated evidence. So, for example, in our classifiers, terms are associated with weights, and as you can see in this example, the term decline is highly positively weighted, despite this being a classifier trained to find vertebrate population trends, where all trends are of interest. So a researcher may therefore want to mask out the decline term to mitigate its influence, and so hopefully reduce any biases in the subsequent data collation. I think this is a pretty interesting area of research, and that clearly further work is needed before we fully rely on automated workflows for evidence and data collation. So that's everything from me. I just wanted to thank you for listening to this talk, thank my collaborators for the work that we've been able to produce, which you can see here for the paper and our GitHub repository, and I'd be happy to try and ask any questions which you may have.
Brilliant, thank you so much, Richard. Apologies for my face obscuring your video there. Someone who helps to organise a technology conference has a problem with technology. Really fascinating talks there, that was really interesting. Thank you all so much. I'd like to welcome you all back to have a bit of a panel discussion about the content of those talks. So I'd open it up to the presenters if you have any questions for one another first. There's some questions coming in via Slack, but I'll let you have a bit of a chat first. Anyone have any questions or comments?
I've got one, I guess. Sorry, Neal.
No, go for it.
I guess it's funny. Like, so the software I presented is doesn't do anything near as clever as what everyone else is doing, which is this sort of updated classification as you mark individual records as relevant or irrelevant and reclassifies whether you've done enough work. So I'm not big in that space, and I think it's a really fascinating one. How quickly is this moving? Like, is it do you feel like the evidence is that we're getting to a point where we know best practice and that we're, 80%, 90%, 5% confident that we can trust this software, or is it diverging? We're getting new methods that will need testing. I wonder if anyone has a view on that.
If I might respond, I think there's a lot of work done on improving the accuracy of these classifiers, and a lot of this is filtering down from work in natural language processing, which is, even in the last 2 years, has had really quite big advances. But I think there's not so much work done on generalizability and how much we can trust this. So I think that's the gap that I've been trying to fill, is to say, okay, let's set a let's approach this from a kind of probabilistic way, and without too much technical stuff, and try and put it in terms that non-machine learning specialists can understand. So with hypothesis testing, and the maths there isn't that fancy at all, really. And it's just trying to say, okay, if I can accept this level of risk, and you can set this yourself, of missing this many studies, and this is also a flexible parameter, then I know, based on simple enough probability theory, that it's safe to stop. And I think none of these workflows are integrated into kind of proper systematic review guidelines. And I think it requires more work to think through under what circumstances it's still a good review, dependent on how you've applied machine learning. I think the point that Richard raised is that sometimes we have there's a kind of false trade-off. So if we don't use machine learning, we're still not doing everything perfectly. So I think comparing your results to searches was a really interesting thing to do, because you can restrict, you're always not screening everything. You're always not looking at every document. And there's a balance between what you do with machine learning and what you do with searching. And I think the different implications of all of those need to be thought through together.
That's a really interesting point. Thanks very much, Max. Yeah.
Arindam wants to make a point.
Oh, sorry, go for it, Aaron. Oh, you're still on mute. There we go.
So have you done a formal confusion matrix and tested your sensitivity and specificity of your classification algorithms? What did you find? Because you know, when you say that you're doing a screening, some kind of a classification of what goes in, what should not go in, and the standard practice, of course, is that human curated lists of references, and then they get into, you know, based on the inclusion exclusion criteria. So then they, you know, these are excellent tools that you've shown us. So the question then is, if you wanted to construct a confusion matrix, what would you see? Was that done in any of the works that you've done? Or is there a need for doing that?
I mean, if I can answer a little bit, I think there are some different approaches that you can do. So one thing you can do is you can screen a random sample of documents and then make a classifier. And then you can assess the performance of that classifier against the documents that you've already screened, and make inferences about how well that classifier will perform on the documents that you haven't screened. And that you can do with confusion matrices, and you can assess sensitivity and specificity. The approach that I was doing had a slightly different objective, in the sense that it wanted to maximize sensitivity, since low performance on sensitivity is particularly problematic for systematic reviews. So it tried every document. Basically, we can set a threshold for sensitivity and test that level of sensitivity has been achieved. And then specificity. So we know that sensitivity will be achieved no matter what. And specificity, the only thing that's dependent then on model performance is specificity, so work savings. So if your model is working really well, you'll save a lot of work. And if your model is not working well, you won't save much work, but you'll still achieve good sensitivity.
Well, thanks very much. I've got some questions coming in via Slack, which I'd like to hand over to you. The first one is from Wolfgang Wichtbauer. Thanks, Wolfgang. Is there any work that the panel's aware of on automated information extraction, so coding effect size computation from a set of studies? Seems like a very hard problem. So what we've mostly been talking about so far is eligibility. But Max, I know we've talked before, I've heard you speaking before about extending these algorithms to look at classifying studies not only as relevant or not, but also based on the kind of content that they have. Can you speak about that a little bit?
Yeah, so I mean, there are something, I think, is it robot reviewer perhaps? I think there is a classifier that extracts some things about bias, risk of bias, if I'm not mistaken.
And also classification of randomized control trials in healthcare seems to be fairly robust these days.
So that's one example. I think that works better where you're dealing with quite standardized pieces of literature, where we have trials with effect sizes. In my work, we've been looking at classifying just basically the topic, but instead of using topic modeling, where we already have a typology with different kind of topics that we're interested in, using supervised learning to classify those topics. But it's not strictly speaking information extracting. It's a kind of tagging.
And it's worth mentioning as well, these methods are almost exclusively based on abstracts, not full text, right? So there are issues around there being a lot more richer information in full text, but it often being locked away in a more challenging body of text to extract. And then also potential risks with reporting bias and overestimation in abstracts. And the fact that lots of abstracts are very heterogeneous in the way that they summarize as well. So there's some underlying assumptions there that are worth noting.
It's an interesting point though, in the sense that extracting data from full text used to be really hard and still isn't straightforward, but it's much faster now. Like even in the last year or two, the software that's out there, and I'm talking about doing this in R, like it's not like you need to code in Python or C or anymore to be able to do that. I think we're probably only a year or so away. Obviously getting full text is still a pain, and you don't want to force people to web scrape or break their, the rules of the various services that we use, but it might be that in 6 months' time, someone starts just doing full text topic modeling or screening routinely. It's quite an interesting thing to see that just how quickly that's accelerating.
It's a really good point. This is actually the focus of one of the ongoing evidence synthesis hackathon online projects called DOI to Text, which was being led by Eliza Grames and involved Matt Granger and Gabby Palomo and myself. And the idea is to go from a DOI to scraping full text from XML or HTMLs, and then subsectioning the text into methods, results, background objectives, those kind of things. We were quite surprised at, firstly, how many records that we started looking at had XML or HTML versions, because the challenges of parsing text out of PDFs is really messy. What you end up is often nonsensical. And there are some great tools if you navigate to the DOI to Text project page on the Evidence Synthesis Hackathon website. You can see you can link to the GitHub and see the kinds of packages that we're using behind the scenes. Yeah, I think you're right that there's an increasing number of open access papers that makes it easier to access the text. Increasingly a move towards HTML or XML, primarily for these purposes, I guess, or often for these purposes. Yeah, I think there's really interesting discussions to be had and thoughts around the quality of information and other challenges we might have around there being so much text in a full text and often citations that are potentially highly irrelevant. Yeah, I share your view of where this is going, Martin. Max?
Is there time to add something quickly there? I think for meta-analyses, so where we're looking for effect sizes and information like that, I think given how critical the accuracy of that information is, I think probably automated extraction is less likely than assisted extraction. So I can imagine something where, often you're extracting the effects from hundreds, not thousands of papers. That would be a big meta-analysis. And I think the time-consuming thing is finding the effect sizes within the full text. And if the computer could say, this looks like an effect size, this looks like something to do with randomization, is this, it can speed up that part of the process. I think that might be more realistic for me.
I think it's also worth just putting a pin in here that whilst we try to build these tools and improve the ways that we're able to better automatically recognize bits of information in text, there's also a parallel approach from the other direction of trying to make primary research more synthesizable. And there's a talk on this in the next session by Emily Hennessy. There's lots of other people working on trying to improve the type of information, type of data, and openness and understandability of the data that's in primary research. So we could face a problem with, or face a solution in the future where those two converge and it becomes much easier to identify what effect sizes are and avoid problems of reporting bias, I guess, as well. Aaron, you need to unmute yourself.
Yeah, there's an issue with the effect size as well, because not all studies will provide you with similar kind of effect sizes. Many people provide very sparse effect sizes. Sometimes they give you probably only coherence D and things like that. I mean, things that need to be properly then reanalyzed. And that becomes a challenge. So it's okay where the effect sizes are kind of uniformly presented, but that's not always the case. So that will be quite a vexing problem. Tricky.
Yeah, good point. It's worth mentioning as well, there's a huge body of work by Ian Marshall and Byron Wallace. We were hoping to get Byron to join the panel, but it's unfortunately in the middle of the night for him. But if you're interested, their work is really, and other people as well, but their work in particular is in the front of my mind because I've been in contact with Byron recently. We have a couple more questions, that if I could jump over to those. Will Ovenden says, Max, thanks for the great talk. Could you just clarify what you mean by when it's safe to stop? Does the algorithm not need to predict every title abstract found in the literature search? And what's the name of the algorithm that you're using?
Yeah, so the stopping criteria is independent of the algorithm. So you could use support vector machines, or you could use BERT, or you could use whatever text classifier you want. And this basically is trained on ones and zeros, which are the relevant, not relevant decisions that you've made. And the features are the title and the abstract. And it makes a prediction for every other abstract that has not been screened. And this simply defines the order that you screen the documents. So at every point, or at every 10 documents, let's say, you can retrain the algorithm, and then you reorder the documents, and that simply decides the order that you screen them. And after every document that you've screened, the stopping criteria is dealing with, okay, based on how many documents I've screened, how many documents there are remaining, the distribution of relevant documents in the documents I've screened recently. Can I assume that we have reached our recall target? Or if we want to be certain that if we want to be more sure that we've reached our recall target, should we keep screening? And that's the kind of decision that it makes. I hope that's somewhat clear. I
think so. That was great. Thanks very much, Max. Something just occurred to me that I wanted to mention as well, if I may jump in, that these algorithms that help to prioritize the likely relevance are being used by a number of review management tools. So these are software, often web-based, that help support the whole process of a review. And there are several different ways that they can be used to differing amounts of how much you hand over things to a machine. And the entry-level one is to still screen everything manually, but to have the machine push what it thinks is likely to be relevant higher up in your list of articles as you're screening. So the ranking is done based on likely relevance. And so you reach a point, as Max's whole presentation, you have this asymptote of at some stage you found everything or most things, and you're only looking through irrelevant stuff because of what the order of what you've seen has been ranked based on an algorithm's assessment of relevance. So the one thing is that then streamlines your pipeline in theory, so that you can move on to the next steps of a review while some unfortunate soul is screening what is almost exclusively irrelevant stuff, and that's for an interesting option for streamlining while you still have that very high theoretical level of rigor that's demanded by some of the review management bodies at the moment that ask for every article to be screened. And then you can use the machine increasingly, whereas the other end of the spectrum is that you're only actually manually reading a little bit and the machine reads everything else and you have these stopping criteria. But that, Max, do you want to respond to that?
Yeah, I mean, if I may make a comment on that point, you can use heuristics for deciding when to stop. So you can say, all right, I'm going to stop after 50 consecutive irrelevant documents, or 100, or whatever that might be. And we tested these types of criteria on the on existing systematic review datasets, and sometimes you end up with terrible recall. So you can have a rule like this, and you can miss 90% of all relevant documents. And basically, it's a really simple decision rule, this 50 irrelevant documents, that's totally dependent on how well your machine learning algorithm has performed, how many relevant documents there are in your set, how big the set is, and it's it's really not a good rule. And the rule that I've presented, I think it might not be the most efficient rule, so I think it can be improved actually, but it's at least reliable, that you can say, I'm sure, well, I'm 95% confident, and I think as scientists we're used to making statements like that, that we haven't missed more than 5% of the studies.
Yeah, that's a really good point.
If I can ask, I think we've still got another few minutes. So, I mean, that's a really interesting point, Max. Like, this seems to me to be a sort of microcosm of the conversation we were having earlier about R packages in general, which is that we're going to end up with a lot of algorithms at some point, and I'm sure some will perform better than others, but you see this in natural language processing a lot as well. So I've seen some work in topic models where people say, oh, well, what's the term that best represents a given topic? And it's like, well, we're not sure, so here's 5 different algorithms and what they each prioritize. Is there some sort of would it be silly or useful, do you think, to sort of smorgasbord this problem and say, okay, well, 3 of our 5 algorithms say you can stop screening now, but the other 2 don't, and you can, or are we just sort of avoiding making a decision by doing something like that?
I think it's hard to combine that with an active learning pipeline, because the maths gets very complicated, because you know, the criteria that I showed was just based on, it didn't look at the performance of the algorithm at all. So you could make a different criteria as you're suggesting. So, okay, how well has the algorithm performed on this set of documents? But this set of documents doesn't represent the set of documents which we're going to predict on. So how informative is the information about past performance, about how informative is that about future performance? I think that's the really tricky thing when you're combining active learning with these algorithms, with an algorithm performance-based stopping criteria. So I think if you're going to use those, if you're going to have an algorithm performance-based stopping criteria, what might be more sensible is to screen a random sample, get an algorithm performing quite well, then select a set of documents that you think, based on past algorithm performance, represent at least 95% of the remaining documents, and then screen those and then stop. So rather than having a kind of stopping rule that's reassessed at each point, I think you would rather do something that's definitely assess the model on a representative sample, then use that model to select documents and then screen the rest of those, knowing that some of them would not be included.
So it's not as modular as we might like that in that context. Righto, good to know.
We have one more question coming in, finally getting around to it. Alina Takola asks, thanks for the talk, Richard. Is it possible to classify studies as empirical versus reviews? Bearing in mind that Web of Science has already something like this, but it's not always very reliable.
I guess, well, I mean, yeah, fundamentally, yeah. I mean, if you have enough information, you can train a classifier to do distinguish between particular groups that you're interested in. So if you are manually going through these results and you see that a lot of them cluster into particular categories and you're interested in finding only one of those, you could then subsequently, I guess, yeah, refine your classifier and try and predict those only and resort the ranking. But it's, unless there's either a pre-trained model or a way of doing it with the sort of unsupervised topic modeling, it's going to require some additional manual input initially to get that off the ground, I think. But Max, did you have a point?
Yeah, I wonder how Web of Science generates those labels. And then I think, well, probably they have a classifier and it performs with not 100% accuracy. And I think your point is absolutely worth recognizing, that you can make a classifier for everything and it will perform quite well. Like natural language processing is good enough that if a human can label something based on that information, then unless it's a very abstract concept, then usually a classifier will be able to perform fairly well at the same task.
Thanks very much, both of you. It reminds me of a comment in a very old, very famous British winemaking cookery book that says you can make wine out of everything, but it doesn't necessarily mean it's going to be palatable. And I think some of the ways that they classify reviews and different types of studies in bibliographic databases comes from the table of contents from the journals. But there must be variability amongst publishers. That means they must have to do some kind of assessment. There is also, it's worth bearing in mind, information specialists will point you towards what are called search filters, which are basically chunks of search terms that have been validated. So there are search filters for PubMed, for example, that can highlight reviews, meta-analyses, literature reviews, and they've been validated by information specialists. That doesn't necessarily mean they only find reviews and they find all reviews, but they've been validated to some degree manually. So again, that comes back to this discussion that you said, Max, about, you know, if we're not reading everything in a bibliographic database because we're using searching, can we perhaps have a broader search and then make more use of machine algorithms? And I think that comes back to a similar point, that this way that we identify literature for literature reviews, evidence syntheses, meta-analyses, is two fairly inefficient processes by necessity, the searching and the screening. And I think what we're going to see over the next years is that those become a little bit more combined as databases become more open, they get bigger, we get more rich information from databases like Microsoft Academic Graph, and the computational tools get more powerful as well. I think it's really exciting. So we don't have any more questions coming in by Slack. I can't see any more on Twitter. But Max, did you have a comment there?
Oh yeah, I was just going to comment on that point about the databases. That, I mean, no one's recommending that we only use Google Scholar, but I think when we think about algorithms, they're kind of already there. And so when we are searching, then that process is not independent of machine learning algorithms. In fact, it's already tied in there, we just can't see it. So I think it makes a lot of sense to try and do this process ourselves if we have the capability to do that. And I think it's not too complicated to implement. I think there are various ways that you can implement this without even having to do that much coding. But I think we need to have sort of capacity to understand what algorithm performance, how to assess algorithm performance, and how to understand the implications of that for our work.
Yeah, it's a really good point. And again, it reminds me that often you see in systematic reviews, people say they search Google Scholar as an additional resource, and they just look at the first, or Google, they look at the first 200 records, or they stop when they stop seeing relevant things after a certain point. And that's exactly the same process. You are using, with Google and Google Scholar, it's a black box unknown ranking algorithm, but you're using an algorithm that ranks records based on the terms you put in, and then you're stopping at a certain point. So anyone who's used Google or Google Scholar in that way in a literature review is already using machine learning and text analysis and algorithms, which I find quite interesting. But yeah, and it's the same with searching, as you say, not to steal your point. Great, I think we don't have any more questions coming in. This is a really interesting session, and we've had over 100 people watching. We've got 96 watching right now, so that just goes to show how interested people are in this topic. So thank you so much to all of you speakers and for joining for the panel discussion. And thank you everybody for tuning in. We'll be back in half an hour, 29 minutes, for the second session on automation. So we will see you then. Thank you.